Section 7.2 is on transformations of exponential functions, and this is kind of a common theme that's reoccurred throughout the book, transformations of parent graphs. So for instance, last chapter we looked at the parent graph y equals the square root of x. And if I add 3, and that's attached to the x under the square root, that should actually move the parent function 3 units to the left. If I plug in -3, now I'm going to get out 0. If I add 3 and it's outside of the radical, so if this is not attached to the x term under the square root, well, now if I plug in 0, I get out +3, so that's going to move everything 3 up. We looked at if a negative was placed out in front, so if it's not really attached to that x term, it's not under the square root, but it's just placed out in front. Well, now, I mean, like if I plug in, let's see, 4, I'm going to get out -2 instead of +2. So this graph would look like the parent function, but it would be reflected over the x-axis. And then this last graph, you know, I don't know if we looked at this last chapter, but if I put a negative and it's attached to the x and it's actually under the radical sign, instead of reflecting over the x-axis, what's going to happen here is, well, now if I plug in 4, I get a non-real number. But if I plug in -4, well, the opposite of -4 is +4, and the square root of +4 is 2. So this graph would actually reflect over the y-axis. So all your x values are changing. It would cause a reflection over the y-axis. So keep in mind these transformations as we move forward. So let's look at the parent graph y equals 2 to the x power. This is an exponential function. Your growth factor is 2, x is in the exponent, and this would kind of be like 1 times 2 to the x power. So if you graph it, it's going to look something like this. Your y-intercept would be 1, 0, 1. So if this is my parent function, I want you to think about what this equation would look like if I translate it 5 units to the right, and what I'd have to do to that equation if I want the parent graph to translate 7 units down. So pause the video, think about what the new equations would look like. So here are actually the new functions, same thing that's happening with a square root graph or a parabola or a cubic function or a line. If I want to move the parent graph 5 units to the right, I just need to subtract 5 to the x value, which for the exponential function, that's found in the exponent. If I want to move something 7 down, I just subtract a 7, not attached to the x, just after that 2 to the x power. You could check, you know, on your parent graph, we said if I plug in 0, I get out 1, 2 to the 0 is 1. Now, for this function right here, if I plug in 5, then I'd get out 2 to the 0. So if I plug in 5, I get out 1. This point is actually moved, so this point right here is actually moved 5 to the right. And then here, let's see, well now if I plug in 0, 2 to the 0 is 1, 1 minus 7 is -6. So from my parent graph here, that point's moved 7 down. So that's one way to kind of think of what's going on. So now I've just drawn a rough sketch of each of these functions. All of these look like the parent graph. They're just being translated. If I want to find the domain, I want to know, well, what can I plug in for x? Well, I mean, here I can take 2 to any power and get out an answer. So same thing here. I could plug in anything for x, and I should be able to get out something for y. If you look at the graphs, they're continuous left to right, meaning my domain should be all real numbers, or -infinity to infinity. For the range, I want to scan up and down. So if I look to the parent graph, notice that I'm never going to quite get out 0. I can't raise 2 to any power to get out 0. So for my parent function, the range is 0 to infinity. And if I just slide the graph 5 to the right, the range is still 0 to infinity for this graph y equals 2 to the x minus 5 power. So asymptote is still the same if I just slide things 5 to the right, the range doesn't change. Now, if I look down to the second graph, the domain, well again, I can raise 2 to any power and then subtract 7. But my range, if I'm subtracting 7 and the graph's actually moving down, now my range is going to be -7 to infinity. So this asymptote has moved down 7, since from my parent graph I've moved that down 7. All right, so I have asymptote y equals 0 here, y equals -7 here. Now how do I find the y-intercept? Well, to find the y-intercept, you want to plug in 0 for x. So any point on the y-axis has an x value of 0, so I'm just going to insert 0 for x into my equation. 2 to the -5th power would be the same as 1 over 2 to the 5th power, and 2 to the 5th power is 32. So my y-intercept would actually be 0, 1 over 32. Which seems reasonable if I look to my graph. Yep, that's going to be a pretty small y value. On the second graph, to find the y-intercept, plug in 0 for x. 2 to the 0 is 1. 1 minus 7 is -6. And yeah, that was the point that we talked about earlier. So these are kind of the key points of each of these graphs. Oh no, oh goodness, it seems like my track flip chart somehow got mixed into my Algebra 2 flip charts. Excuse me, let me switch the page here and... Okay, there we go, now we're back on track. So same parent graph, y equals 2 to the x power. What would the new equation be if I want to reflect this over the x-axis? So think about this, pause the video for a moment. If I want to reflect the graph over the x-axis, I just need to throw a negative out front. So here's a table with the graph of my parent function. If I have a negative, all that would really change is, now I'd have something that looks like this. Now, I want you to keep in mind, this is not in parentheses. It's not saying -2 to the x power. This is just read the opposite of 2 to the x power. So when I see something like this just means the opposite of 2 to the x. So whatever I got out before, 2 to whatever power, now I'm just taking the opposite of it. And if my x values stay the same, but my y values change, what's going to happen is this graph would just flip over the x-axis. So that negative is going to cause a reflection over the x-axis. My domain, I can still plug in anything for x. But now what's happening for y? Well, now I'm only getting out negative values. So this graph is going to decrease forever. So the lowest it's going to reach is -infinity. Highest it's going to reach, I'm still going to approach 0, but I'll never quite get out 0. The asymptote for both the parent function and the reflection would be the x-axis, or the line y equals 0. And your y-intercept now, if I plug in 0, I'm actually going to get out -1. So now, oh goodness, again it appears that my track slides, more of them got mixed in here somehow. Look at how much fun these girls are having. All right, continuing on. So what would these do? What if my a value is not 1? Or what if that initial value changes? Well, think about, okay, let's go back to the parent graph of, what did something like this do? Well, that just vertically stretched your square root graph. So same idea here, if I'm multiplying by something that's bigger than 1, this is just going to vertically stretch the graph. Ooh, this is not really to scale. My new y-intercept would now be 0, well 2 to the 0 is 1, 1 times 4 is 4. So now my y-intercept would just be 4 times as high. if I had a half out front, that would cause a vertical compression. And now if I plug in 0, well, 2 times 0 is 1, 1 times a half would just give me out a half. My y-intercept or my y values would be half as large as they are on the parent function. So if that a value is greater than 1, that would cause the parent graph to vertically stretch. If it is in between 0 and 1, you're going to have a vertical compression. If it's negative, then you're going to have a reflection in there also. So here's just one last, more specific graphing example of how a transformation would affect a parent graph. So again, we're starting with that parent graph, y equals 2 to the x. I plugged in x values to see what came out for y. So these are some coordinates that I plotted for the parent function. And then if I add 1 to the x, well, I would be expecting, okay, if I add 1 to the x, this should shift the parent graph 1 to the left. So I could take all the points on the graph and move them 1 to the left. We can actually give this a go here too. So if I plugged in 0 for x, let's see, I'd have 2 to the 0 plus 1. I'd actually have 2 to the first power, which would be 2. So 0 now maps to 2. And I can see, yep, this point on the parent function is now actually moved 1 to the left. If I plugged in 1, well, now that's actually 2 squared, or 4. So if I plugged in 1, I get out 4. Sorry, had to adjust my parent graph there. So if I have 1, I get out 4. That point from the parent graph moves 1 to the left. And you could fill out this table completely. And then you could see for certain that that parent graph is moving 1 to the left. Last thing again, if that negative's out front, that would just change the sign on all your outputs. So now if I graphed, all of these points, 0, -2, and all the rest in the table, that should just cause a reflection over the x-axis.